Hello, morning everyone. I think the title I was given was atmospheric chemistry, but I've changed it to atmospheric composition because it's more than just chemistry. It's more than just gases floating around that we're really interested in. That's a nice picture of an ozone hole simulated by ACCESS, I think. I nicked it from one of Fraser's slides, so I'm not sure if it is or not. Yeah, so really, the place I wanted to start with this presentation was by telling we already have a composition modeling capability within ACCESS and have done for a long time, and that's probably a feature that's not been widely recognized. The current model is based on, or it's an extension of ACCESS-CM2, so we call it ACCESS-CM2 Chem. So it's got a full chemistry, so tropospheric and stratospheric chemistry scheme added on top of ACCESS-CM2. So we've got all the benefits of ACCESS-CM2 plus some chemistry. There's the usual list of descriptions. One useful thing to point out is that we can also nudge ACCESS, not just ACCESS-CM2 Chem, but ACCESS-CM2 with reanalysis meteorology, and that's a really useful tool to have, especially in composition modeling, but it's potentially useful for a wider audience as well. The history of this composition stuff actually goes back 10 years or so in Australia, with a couple of different iterations of ACCESS. Some more ACCESS-like, some less ACCESS-like. ACCESS-CM2 Chem, that little screenshot there is a paper just published, in fact, in JSHES, written by Fraser Dennison, and any further details can be grabbed from there if you like. It's probably worth talking about what chemistry and aerosol is, and the place to start is around some nomenclature. So UKCA is a word or a little phrase that gets bandied around. It stands for United Kingdom Chemistry and Aerosol Scheme. And really, it's not a chemistry scheme in itself. It's the framework for doing all the composition, whether it's aerosol, whether it's the chemistry in the troposphere or the stratosphere. So trying to get away from using UKCA as a shorthand way of saying chemistry, because it's not really just about the chemistry. No need to really dig into the details, but suffice to say the full chemistry is a pretty full representation of the climate relevant chemistry processes, so troposphere and stratosphere. It takes about 90 traces to represent that in the model. You could have more complicated schemes that easily go to hundreds of traces. 90 traces is already very expensive, as I'm sure you're aware. I'll get to that expense in a second. One of the big differences between ACCESS 1.x and ACCESS-CM2 is the inclusion of GLOMAP. So there's another 20 traces that are required to carry around the more complicated, more sophisticated GLOMAP aerosol scheme, even with that in mind, we're still not capturing stratospheric aerosol in ACCESS-CM2. So there's a bit of a gap there, is what I'm pointing out. Oops, excuse me. It's worth pointing out that both the chemistry and the aerosol are coupled to, well, the chemistry isn't coupled to the cloud, but there are couplings to the cloud and radiation scheme. So the first and second direct effects and the indirect effects. Sorry, the other way around. And I haven't written on there, but they also affect large-scale rainfall. So there is a coded connection between aerosol, clouds, radiation, precipitation that's represented in the model, and that enables feedback processes. So GLOMAP's the aerosol scheme, also known as the reason why ACCESS, or one of the reasons why ACCESS got expensive between 1.x and CM2. It's those 20 traces that we're now forced to carry around the more complex aerosol, compared to the 3 or 4 traces that were previously required in the classic aerosol scheme. So obviously you kind of have to motivate, why is that necessary? You know, what benefit do you get out of that? And the answer for Australia was, that's what we were given from the Met Office, really. I could spend more time perhaps explaining to you the benefits of having the more complex aerosol scheme. But the plot I haven't shown is the IPC forcing plot, the summary of the forcing. So you've got the CO2, the methane, the ozone, and you see the aerosol one, and it's always had error bars about that big, whereas all the error bars are out that big. And it hasn't changed between AR3, 4, 5, 6. They've always been big. And that's because we're not representing a lot of the processes in aerosol. So that's the short version of why it's useful to have the aerosol scheme. always useful to have the aerosol connected to the clouds and the radiation and so on and so forth, even if we're not quite getting that that uncertainty down as much as we like. Even if you have no interest in chemistry, you know chemistry is expensive. It's sort of the first thing that comes up. So there's a bit of a summary of how expensive it is. So the number in red there, it's about, including chemistry on top of CM2, adds about a factor of 1.9 to your CPU hours. So not insignificant. Not insurmountable, not insignificant. If you run without the ocean, you get a slightly faster speed up, but the big number there is the factor of 1.9. When you compare that sort of 3.1 years per day with the chemistry to the ESM 1.5, you get a stark sort of difference, 15 years per day versus 3 years a day. So having the chemistry possibly means we're really limiting the number of ensembles, the size of the ensemble that we can undertake. So to sort of go back a little bit, why are we tolerating this expense, or why am I asking you to tolerate this expense? That's a picture from it's a process representation of what's included in UK ESM. So UK ESM obviously includes the full UKCA chemistry and the aerosol as well. Basically, I like to think of the composition as a sort of connector between different components of the Earth system. So the age-old thing or process has been DMS, dimethyl sulfide from the oceans, influences clouds and so on. What's probably not clear on this plot is things like VOCs, other aerosol sources, both from natural and anthropogenic sources, methane lifetime. Ozone is the third most important, tropospheric ozone is the third most important greenhouse gas. We've got stratospheric ozone, and ozone depletion resulting from CFC release in chemistry. And because this is it's a UK focused plot, it completely omits any ice and completely omits any, tiny reference to the oceans there. So this is from a paper just accepted in Elementa Science of the Anthropocene, just to again show some of the more or less obvious things or pathways where aerosol and chemistry is important. So trace gases released from the open ocean and the marginal ice zone contribute to aerosol. We have sea spray, which can contain organics. There's a biological link there, contributes to aerosol. What we isn't quite explicitly shown here is that aerosol can carry things like iron, phosphorus to the remote oceans. So there's potentially a feedback in the Earth system acting through aerosol and composition that we don't capture in our Earth system model as it currently stands. And of course, all of this has an impact on clouds and cloud phase, precipitation, and that age-old southern ocean radiation bias problem we're still carrying around in our model. So that's a short motivation for why we should perhaps care about chemistry. Just a bit of a plug for some work that Fraser did with the CCMI initiative, the Chemistry Climate Model Initiative. So basically, it's like a CMIP for chemistry models, essentially. So a couple of simulations that Fraser did, RefD1 and RefD2, a hindcast simulation, which was constrained with prescribed sea surface temperatures, so like an AMIP-like simulation, and simulated over basically the ozone hole time period. And then a simulation with a coupled ocean that actually looks forward in time as well. So it runs that pre-ozone hole period from 1960, but looks out to 2100 for a particular scenario. And that enables us to look at ozone hole recovery, so ozone hole formation and then ozone hole recovery. So a bit of a plug for that. In doing that work, we found out our model, ACCESS-CM2 Chem, does a really good job. Compare the red squiggles to the black squiggle, and then compare that to the blue squiggle. Blue is old, red is new model, black is observations. Looks good. And in that JShesh paper, one of the points that comes across is you actually simulate the SAM trend better, I should say the stratospheric SAM trend better with coupled chemistry than you do without. So there are benefits all around the model to including explicit chemistry. I probably won't get to talk about this very much, but we're talking about hydrogen as a way of displacing carbon in the economy. Hydrogen's chemically reactive. It will have implications for atmospheric chemistry, methane lifetime, stratospheric ozone, tropospheric ozone lifetime. It's significant. There's a major body of work addressing the Southern Ocean warm bias, and that doesn't include just modelling work. That includes multiple ship campaigns that are using the, nearly said the Aurora, but using the Noina when it comes back, and the Investigator to really dig into some of the process-related stuff happening in the Southern Ocean. So that's potentially lost unless we have an outlet for it within our models. Future CCMI, and the thing I always say, what happens when we have the next Pinatubo in us? What happens to Australian weather and climate when Pinatubo goes bang? Or indeed, next Tonga Tonga. It's going to happen eventually. We need to be prepared for that. So not necessarily CMIP7 relevant stuff there, but actually really quite important stuff, I think, for Australia, Australian capability. The discussion points, well, to chem or not to chem, is it a question? Can we afford it? Maybe it's not even a question for CMIP7, but I would say absolutely we need it in our research capabilities. Does Australia, this is a provocative one, an Earth system model or an Earth system model? I'll let you read between the lines of that one. And like I say, do we have the ability to push these models through our infrastructure? Yes or no, I don't know. So I'll leave those up on the slide and then take any rocks thrown at me. Thank you.